Welcome home, sir. You need to pay attention to control the time today. With every passing hour, I remind you once. Enjoy your time, sir.
Hark, the chronicles continue. Part 6 cometh. By the hammer of the gods we yet draw breath. When we embarked in Part 1, I estimated our survival odds at those of a snowball in Muspelheim. Yet behold, 6 parts, we are now married to this beautiful disaster till segmentation fault do us part. Welcome back, steadfast companions. Thy presence suggests either admirable dedication to OS craft or concerning enthusiasm for witnessing suffering. Grab thy chalice, coffee, tea, or tears of failed file systems, and settle in. The saga thus far, Part 1, we summoned the bootloader. Chaotic, bewildering. We persisted like fools rushing toward destiny. Part 2, we built core structures. The AI proved both ally and trickster. Part 3, we wrestled memory. The OS stopped being a digital paperweight. Part 4, we conquered interrupts, discovering the line between working and catastrophic failure is thinner than a wizard's patience. Part 5, we descended into assembly, context-switching interrupt handlers. We survived the silicon. And now Part 6, file systems, virtual memory. The abyss has Starbucks. Today we confront the file system, where data persists beyond RAM's fleeting lifespan. We implemented the virtual file system layer, that magnificent abstraction allowing our kernel to speak of files without caring whether storage is spinning rust or caffeinated hamsters. Beneath lies our concrete implementation. We designed nodes tracking metadata, size, permissions, timestamps, reference counts, and pointers. Direct, indirect, doubly indirect blocks. Direct blocks point immediately, larger files venture into indirect labyrinths that would make Theseus weep. Block allocation brought hell. We implemented bitmap allocators where each bit represents one block. Simple. Yet we spent 2 days debugging why our allocator claimed block 4 billion was free on a 65,000 block disk. We confused bytes with bits, sanity with luxury. Our superblock, that sacred structure, contains vital statistics, blocks, inodes, magic numbers. Corrupt this, and thou hast an expensive random number generator. Directories are special files containing entry lists mapping names to inodes. We handle variable length names, deleted entries, and the eternal. And entries that must not point to infinity. The journaling subsystem ensures atomicity. When creating files, we don't simply write a node, allocate block, update directory. Power failure mid-step creates half phantoms and leaked blocks. Instead, we journal, write transaction, mark committed, execute, mark complete. On crash recovery, we replay incomplete transactions, emerging consistent even when power grids behave like caffeinated squirrels. Implementing this required circular logs, sequence numbers, checksums. We debugged race conditions where the journal claimed success, but writes hadn't reached platters. fsync is our slow, mechanical friend. The buffer cache holds recent blocks to avoid disk-seek torment. We implemented LRU eviction, least recently used departs when memory grows scarce. Write-back caching improves performance but risks data loss. Write-through is safe but slow. We chose write-back with periodic sync, balancing speed against power failures. Virtual memory. We transformed our kernel into a sophisticated subsystem providing isolation and infinite memory illusions. Page tables. Hierarchies mapping virtual addresses to physical frames. On x86-64, we traverse 4 levels, PML4, PDPT, PD, PT, 512 entries each, covering 256 terabytes per process. We implemented page table walking in assembly, recursive mapping allowing tables to map themselves. We set flags, present, writable, user/supervisor accessed, dirty, global, each a weapon in our protection arsenal. The translation look-aside buffer caches recent translations. We flush with invoke when tables change, invalidating stale entries. Global pages survive context switches without invalidation, precious optimization in syscall overhead. Demand paging brings pages into memory only when accessed, procrastination in silicon. We mark pages not present. First access triggers fault, our handler allocates frames, fills from disk or zeros, updates tables, resumes execution. Applications experience merely slight pause, the cost of physical reality intruding on virtual dreams. Copy on write. When processes fork, we share read-only pages. Only when one writes does the handler intervene, copying to new frame, updating mappings, granting write permission. This avoids copying entire address spaces during fork. Memory mapped files. We implemented mmap, allowing applications to treat file contents as memory. The file becomes backing store, reading accesses data, writing modifies it. We handle private mappings, copy on write, shared mappings visible to all, anonymous mappings, no file backing. Swapping. When memory exhausts, we evict pages to disk, our swap partition, freeing frames for active use. We track activity via accessed bit, implementing approximate LRU. Writing to disk is slow. We batch operations, cluster adjacent pages, pray the disk controller keeps pace. The page fault handler became our most complex assembly routine, distinguishing legitimate faults from kernel bugs. We decode error codes, present page with wrong permissions, non-present requiring allocation, user access to kernel pages. Misclassification brings crashes or security holes. Debugging required sorcery. We logged every fault with address, error code, instruction pointer, megabytes of traces analyzed at 3 a.m. while questioning career choices. We instrumented the TLB, verified invoked calls, deliberately corrupted tables to test recovery. The AI, my eternal companion, initially suggested, just use Linux VFS. It then generated inodes where size overlapped permissions, creating files that changed ownership when growing. Yet occasionally it suggested elegant solutions, radix trees for page cache, red-black trees for VMA management. We are bound together in suffering, like Sisyphus and his occasionally helpful boulder. There were dark moments when the file system refused to mount. Superblock read correctly, yet ls returned phantom files from uninitialized memory. Root directory inode was being overwritten by buffer cache confusion, 2 blocks claiming same cache entry. We implemented proper locking, mutexes for hash tables, read-write locks on buffers, spin locks for free lists. Complexity exploded, yet stability emerged. Another night, virtual memory entered infinite loops, faulting on the handler itself, recursively until stack exhaustion. Our handler's code wasn't marked present during early initialization. We learned to establish identity mappings before enabling paging, to walk before we run. Yet we persisted. Through stubbornness, caffeine, and refusal to admit defeat before silicon, we bent file system and virtual memory to our will. Inodes align, journal commits, page tables map, TLB accelerates, demand paging delivers, copy on write shares, it works. Victories amidst chaos behold. We created a file system storing data without immediate corruption. Files persist across reboots. Our cat displays contents without panics, mostly. We implemented mkdir, rmdir, link, unlink, rename, each hard-won against entropy. Virtual memory supports, per process address spaces, demand paging, copy on write forking, memory mapped files, swap space, protection bits preventing user processes from touching kernel memory. We wrote tests allocating gigabytes of virtual memory on megabyte physical machines, watching the system page without crashing, acrobatics once impossible. Our boot process initializes, physical memory manager, virtual memory, block device driver, buffer cache, file system with journal recovery, first user process with complete address space. From power on to shell prompt, processes spawn, files persist, memory maps. The path forward, device drivers await, keyboard, mouse, display, network cards. Each requires hardware protocols, DMA transfers, manufacturer quirks. Networking looms, Ethernet, ARP, IP routing, TCP congestion control, checksums will calculate incorrectly at 3 a.m. User space grows hungrier, proper shell with job control, standard libraries, applications beyond test programs. But today we celebrate Part 6. We built persistence surviving reboots. We mapped virtual worlds onto silicon. We survived with sanity fragments intact. I summon thee, if this chronicle entertain thee, smash that subscription rune with thousand sun fury. Ring the notification bell, leave comments. Tell me thy suffering, suggestions for Part 7, favorite file system. Thy wisdom guides this series. Share with code warriors, procrastinating students, anyone believing OS development is reasonable weekend activity. Spread word that Part 6 exists, that virtual memory bends to our will. Every view fuels persistence. Every like sustains morale. Every comment reminds us we scream not alone into the void. Part 6 concludes. We exit with file systems persisting, virtual memory mapping, and new psychological trauma. We advanced our art. We were not broken, merely bent. Thank thee for witnessing this journey. Thank thee for patience as I debugged page tables on camera. May thy code compile on first try. May thy files never corrupt. May thy page faults resolve correctly. The compiler be with thee until Part 7, brave souls. Go forth and code. The operating system awaits.